welcome everybody. So this is a Flow seminar where Flow stands for Federated Learning One Word Seminar. And this seminar was created to provide a global online forum for the dissemination of latest scientific research results in all aspects of federated learning, including distributed optimization, learning algorithms, privacy aspects, cryptographic personalization, communication compression systems, hardware, and many more. My name is Samuel Horvath, and I'm one of the organizers, together with Peter Richtarik, Virginia Smith, Aurelian Bellet, Dana Listar, and Sebastian Stich. So today is my great pleasure to introduce our speaker, Holger Roth, who is a principal applied research scientist at NVIDIA, focusing on deep learning for medical imaging. Over the past several years, he has worked closely with clinicians and academics to develop deep learning-based medical image computing and computer-aided detection models for radiological applications. And his research includes computer-assisted annotation methods, active learning, automated machine learning, and collaborative model development techniques, such as federated learning. And today he's going to tell us more about how to apply federated learning for medical image analysis. So thank you, Holger, for agreeing to give a talk. Looking forward to it, and stage is yours.
Hey, thank you very much for the kind introduction. Yeah, as the title indicates, I'm focusing mainly on the use case of federated learning for medical image analysis. And in healthcare applications in general, we want to build very robust and generalizable models so that they can be applied in clinical practice in the hospitals, right, for clinical workflows. And it's well known that for that, you need to have training data sets that are diverse and capturing really your patient population as the algorithm would see in practice when being deployed in the hospital. So it's important to build up large, diverse data sets spanning different patient populations, different diseases, different scanner types, acquisition protocols, in order to make these algorithms more robust. At the same time, we need to have privacy in mind, and especially in healthcare, there are a lot of regulations and concerns about patient privacy, which is, of course, of utmost importance. So making sure that no private information is being leaked in this AI model development process is very important. So I think, as everyone in the audience can appreciate, we think that federated learning is a very useful technology to address these problems, as it can allow hospitals or research institutes with healthcare-related data to jointly train AI models, therefore making use of the larger data sets that can be built up in using these federated learning consortiums without having to share their data. So they can get around some of the privacy and data regulation issues by keeping control of their data locally, and so retaining the data governance. I think also most of the people in the audience are aware of these different type of applications, but this federated learning encapsulates a kind of a wide scope of applications, can be very many variations. In the classical vanilla federated averaging approach, we typically talk about a horizontal federated learning, and that's also where we have done most of our work so far. It's basically assuming that each hospital has a similar data set. They could, in principle, all train their own model locally, and then these models are being averaged using the federated learning. But there are certainly also, excuse me, there's certainly also applications of vertical federated learning or heterogeneous federated learning, where you could think of one client being a hospital and the other client maybe being the pharmacy, or some lab that holds some blood test values for the same patient. So there you need to have some kind of common user base. In this case, it's a common set of patients across the different hospitals, and then we can build hopefully more powerful models that can make use of all this available data for the same patient in order to make better predictions. Again, even acquiring the data is very expensive in healthcare. So especially if you talk about annotated data sets, it's very time consuming, right? You need to have expert annotators like radiologists, clinicians to find the relevant areas in the image if you're talking about segmentation models or detection models. Go ahead.
There's one question that appeared in the chat by Anupam. I'll try to unmute Anupam about the data.
Yeah, my question was around regulatory, in US there's HIPAA, right? So is sharing the gradients instead of the raw data, is that allowed under the regulatory requirement?
And so we have done several real world federated learning studies which show that it is possible, and with the current regulatory processes, of course, you need to have like individual hospitals agreeing to joining this study. So there's an IRB, so internal review board meetings and stuff like that need to happen for these studies to be approved. So in that kind of study proposal meetings, you need to make sure that you can guarantee certain privacy, or you can make certain privacy guarantees, right? Which then reduce the concern about data leakage and things like that. I will actually have a little bit of a couple of slides around that topic as well in the end. So yeah, it is currently possible, but I think regulators are also becoming at the moment more aware of this technology. So there might be adaptations in the law, right? But currently with the IRB process, we definitely have been able to apply these kind of techniques in practice. And okay, does that roughly answer your question?
Yes, it does. Thank you.
Thanks. Okay, so then again, I was talking about the difficulties of even building up data sets, right? And then these federations can have hopefully an impact into allowing or in making it easier to build up large data sets as part of this federated learning consortiums. So there can be even applications of multitask learning where you start maybe with a global model and then fine tune on different downstream tasks for different applications at these hospitals. And then again, important for regulatory processes like FDA approval in the US, right? When you actually want to deploy your model in the clinic, you need to provide a lot of evidence that this model is robust. So having these federated learning consortiums is very useful for showing a lot of evidential data that shows that the model is robust and generalizable. Okay. Also, there are these kind of more technical differences. So I think everyone is aware of this so-called cross-device scenario, where which is probably the original use case for federated learning, where you have thousands or up to millions of users with low-end compute devices, and also very kind of unstable communication, irregular connections to the central server. So that kind of application is not so much what we are focusing on at the moment. We're more concerned about this cross-silo use case, where we're really thinking of one client being an individual hospital, which has their stable internet connection and dedicated compute, and typically a large data silo, as the name indicates, in the hospital that can be accessed. So in that scenario, of course, the communication patterns are somewhat different, and your infrastructure design choices are also dedicated by what use case you want to explore. But I'm not saying that this kind of cross-device use case is not useful for healthcare, right? You can think about wearable devices or individual scanners that can maybe do federated learning, and where you might have much larger devices, a number of devices. If you're interested in this topic, we have written a kind of positioning paper a few years ago where we go into all the potential benefits of federated learning for healthcare, starting from clinicians to patients, researchers, hospitals, to the scanner manufacturers. Another question?
So we have another question. Yes, by Kumar. Let me just unmute Kumar. Yes. Please go ahead.
Hey, hi, Holger. So my question is about this. So I've never really understood why do something like federated learning for cross-silo settings. Because if you have fewer number of devices, why not learn personalized models for each of these devices based on some sort of privacy-preserving collaborative protocol? So are you guys exploring that direction, or you are capturing it as the usual federated learning setup where you're minimizing the average objective on a set of devices? In the cross-device setting, it's clear, like if you have 1 million or 2.5 billion devices, you don't want to like learn as many models. It's an engineering burden to do that. But in the cross-silo setting, it's not super clear to me.
Right. So you're saying like cross-silo is more, or lends itself more to personalization, right?
Or multi-criterion optimization. Like, I don't know if like federated learning, or at least the usual federated learning, is the right way to capture it.
Right. So the non-IID issue, of course, is an issue in the healthcare applications, and we are trying to study that. Actually, I will show a couple of slides. I think one thing with the personalization is that from a regulatory approval point of view, it might be more difficult to say that you want to approve individual models for each hospital. So from a company building AI models for healthcare applications, it might be easier if they can say they have one model. Of course, in practice, that model could be like an ensemble of personalized models that is somehow then adapted, as long as you can show that it's robust in your test cases, then I think that would be fine. So I think we're probably agreeing that some sort of collaboration needs to happen. If it federated averaging might not be the best algorithm.
Yeah, collaboration needs to happen, but I'm not sure if casting it as a single criterion optimization problem is the right thing to do. Also, I think there's a question in the chat which I also have, like many of these algorithms and designs are motivated by communication bottlenecks. I'm not sure if that also exists in the cross-silo setting.
There are communication issues as well, but maybe less pronounced as for the mobile phone applications. So maybe let me show the kind of research first, and then we can discuss more. Okay. So some of the real-world use cases that we studied for applying federated learning in medical imaging is listed here. So we did an initial study looking at brain tumor segmentation using a public data set. So that was a simulation. But the good thing with this data set was that it is a multi-institutional data set. So we were basically able to find the original data providers for each brain image and split it in a fashion that's very realistic in that sense, right? You actually know each client corresponds to the original data hospital where the data was acquired. So that was basically showing the proof of concept that we were able to achieve a similar performance as in the centralized settings, also applying differential privacy there to reduce the concerns about data leakage when sharing the gradient updates. And that motivated us to then do something in the real world. So we started a study with 7 hospitals in North America and South America for breast mammography prediction. Then about the same time, we also had a prostate segmentation problem in MRI. So that's like these are actually 3D images. We had 3 hospitals in North America joining this effort, and they showed that they could learn more generalizable models. Also, pancreas segmentation for abdominal CT images. I have some more slides there. And most recently, we've done a larger study with 20 sites across the globe for COVID prediction using X-ray and EHR data. So this pancreas example is actually a quite nice illustrative example, because here we had 2 hospitals, like 2 universities, in this case, research labs, who had data sets for, sorry, I can't see my own slide. Yeah, okay, so the client 1 only had healthy pancreas images. So in this case, it would only include the background, so the air and patient body, with the foreground being the pancreas, the organ segmented. While the other client has cases with pancreatic tumors. So in that case, the model was trying to predict 3 classes with the background, pancreas, and a tumor. So now, if you apply the C2, a local model just trained on cases that have pancreas and tumor, that model has a tendency to predict tumors in cases where there are no tumors, right? So it's a false positive. You can see the ground truth here as a healthy pancreas, but the model is predicting the tumor. So that's something we really want to avoid in order to avoid additional downstream treatment and diagnosis tests that need to be run for this patient. So while in contrast, the global model was able to learn from both data sets, right? And then therefore had a better understanding of healthy cases and didn't make that false positive prediction. Similarly, the other way around, we can see that a case with a tumor, of course, if you have a model that's only seen healthy cases for training, it has no concept of a tumor, so it's completely missing that region. While the global model is not perfect in this case, but it at least highlights the tumor region here correctly. Okay, so this largest effort that we did so far was published last year in Nature Medicine. And as you can see from the author list, this has been a large collaborative effort in just getting everyone together to decide on the task, right? Prepare all the data sets on each hospital site to be somehow compatible, and then actually do the training. So 20 sites across 8 countries joined this effort for predicting the oxygen needs for somebody presenting at the emergency department with symptoms of COVID-19. So you can see the model is actually a multimodal model that takes in a chest X-ray, which is typically acquired at a emergency department, and some of the standard EHR values, blood test values, patient demographics like age, to predict the oxygen treatment needs for the next 24 hours and 72-hour prediction. Sorry, is there a question?
Yeah, there's a question in the chat. Let me just about the model. So I wanted you to first finish, but I guess maybe it's also a good time to ask. So there's a question by Konstantin. So Konstantin, please go ahead.
Thank you. So, because I'm mostly working in academia, so right now I'm very interested in your studies. So, can you say, like, what is the optimization problem that you consider? Is it unweighted cross-entropy loss, which is typically used in academic papers, or you have observed that there is a need of some specific weighting schemas? So, what is this question also?
Sorry, can you
yeah.
let me just try to, because the audio was somehow interrupted. You're asking about the specific algorithm that's
No.
used?
What is like? So I have never tackled medical tasks, and actually, people in academia. So when they publish papers, they typically consider, let's say, unweighted cross-entropy loss. So we typically in academia, people don't perform any specific weighting of data samples or data points. So in the medical domain, does it exist some specific weighting for samples?
I mean, for these kind of studies, I would still call them kind of proof of concept, right?
Yep.
Actually try to show that even a simple federated averaging algorithm is giving you some benefit in terms of model generalizability. So the weighting, we kind of follow the standard federated averaging approach and weight by the data set size in that case.
Okay.
Right? So that was done, but like our framework that we used did have options to play around with the weighting. I think we didn't find a lot of benefit from doing it in some kind of heuristical manner. So the federated averaging is actually a pretty strong baseline for most of these use cases that we had so far.
And like in the model for segmentation in the previous slides, which model has been used? Is it like UNet type or?
Yeah, this is typically a 3D UNet that we're using. Actually, our team is also very much involved in Monai, which is an open source platform for medical image analysis, using for mainly focusing on deep learning. And we have basically a lot of these kind of 3D segmentation models published there as part of the framework. So we typically use some model from there.
Okay, thank you. Can you say, just last question? So because my research is in kind of optimization algorithms like convex, non-convex, non-convex. However, I mean, I'm interested in medical domain. Is any real like convex optimization algorithms, like I don't know, connection with machine learning, kind of logistic regression, support vector machine, or it's mostly only deep nets?
Right. It's still being used a lot in non-imaging tasks, I think. So if you have like, let's say you have just the EHR data, right? Then you can probably use some more classical methods to learn from those.
Okay, thank you.
So, yeah, it's still like boosting trees are still very popular, for example. Okay, let me continue here. So here is showing just a kind of real world use case, real world data that we used here, right? Every hospital has very different distributions of the chest X-ray images, and data set sizes were quite varied as well. And also features like the patient age. You can see it's mostly patients with kind of the risk a risk population, right? You know, a little bit more towards the elderly patients. But we also had a pediatric hospital with younger patient population here, which then, you know, helps you build more robust and generalizable models. And we can really see this here if we compare the performance of models that are just trained locally, just using the local data set. Here, the sorting is based on data set size, 1 being the largest. So you can see even the largest client in terms of data set size gets a boost out of using federated learning on their own local test set, right? And then especially if you compare the generalizability of these models. So here we use the locally trained models and apply it on the test data of all the other clients or all the other hospitals, right? And you can see then, of course, models that are trained on small data sets, they don't generalize at all. Here, area under the curve around 0.5 is basically random prediction. And even the largest client gets a boost when compared to the federated learned global model here. So that's like 38% improvement on average in generalizability. And we think this really illustrates nicely that this collaborated effort can help you in build more generalizable models. We then also took that model and tested it on an external test set. So these are from hospitals which were not participating in the federated learning. And again, the model was robust and achieving a good prediction performance for predicting the need for mechanical ventilation, for example. Okay, so yeah, some of these problems we already discussed earlier is about this non-IRD-ness, especially now that we are looking at real data sets. We can see in medical imaging, we really have these domain shifts. Like here, the mammography example, like we're not intentionally, we didn't try to do any data harmonization here to see like how well the model can cope with it. And you can see that, you know, the different scanner devices produce very different looking mammography images. So this is a domain shift in the appearance. And then you also have domain shifts in quantity and also in the label distributions, like the annotation standard might be different across different sites. So for example, here the client 7 has kind of an outlier distribution, right? In that somehow the radiologists there, they didn't apply this label so often. So it's a kind of a subjective task to annotate these images. So we mainly think there are like 2 ways to address this issue. One is personalization, as mentioned earlier. And another useful tool is the automated machine learning or automated federated learning in this case, where we can carefully tune the hyperparameters in the data-driven manner. So one of our recent works on personalization is this federated supermodel. Here, the idea is that we train a model selector that can then, based on the input image, can select which client's model is the most useful to apply. So the data set here was fundus images. Again, I don't have an example here, but if you look at the paper, you can see that a lot of domain differences between the different data sets. Here we used several public challenge data sets that were separately acquired, right? So from different sources. So you can really see this real world domain shift issue. But using this approach, we were able to even outcompete the centralized baseline in some applications, like here the retinal cup segmentation. And this is basically because the supermodel is basically some sort of ensemble, which is even more powerful when compared to a single model trained on the centralized data set. So even if you have all that data centralized, but you have these domain shifts, it's still challenging to train one good generalizable model on that data, right? So this approach seems quite promising. Then on the auto ML front, we kind of started with this work where we also mentioned earlier, right? The weighting of the different clients or different hospitals can play an important role. It's kind of the most straightforward hyperparameter you might want to tune, rather than just using a heuristic as like the data set size. So here we model the aggregation weights as a Dirichlet function. And then every few rounds of federated learning, the local models are being exchanged with each other, with the other clients, and they can then kind of fix the model parameters, but only update these weights, these aggregation weights based on their local data. So that happens in using like a gradient optimization step based in a data-driven way, and then we can average these optimal aggregation weights again. And you can see that the algorithm does converge. So it turns out that the kind of the relative weights are very similar to what a Fed averaging approach would also give you, like based on the data size. But that also indicates that the algorithm is working correctly. And in some cases, you might see maybe a larger improvement compared to federated averaging. Here we still get a reasonable boost in performance, I think, by doing this data-driven approach for learning the aggregation weights.
Sorry, Holger, there's a question related to the previous slide. So by Anupan, let me just unmute Anupan, and yeah, so please go ahead, Anupan.
Yeah, so I was just curious that how did you train that that supermodel? I think the slide before that.
Oh, the supermodel.
So the classifier, and then are the number of your sort of component models equal to the participant organizations? Like, how did you train the supermodel classifier? Like,
yeah, it has been some time. I would recommend you check the details of the paper. Unfortunately, I don't know exactly from the top of my head how it was trained.
okay, no problem.
I guess, yeah. Sorry, I'm a little bit unfamiliar with this work now. But in terms of the number of models, yes, we do use the same number of models as clients in this case. But I think the method itself could generalize to maybe using less than the number of clients, right? You could the selector is actually, I might be speculating now, but it's actually based on
it could be more or less.
On which input image, right, is the most appropriate model. So I think we use the knowledge of where the image is coming from originally, but I might be wrong. But in that way, like if it is actually making the selection based on the input data rather than saying this image is coming from a certain client, right? So then you can actually apply it to like new data sets from different clients, and it would still make a selection from the set of available models. So we that whole, right, and then how the generalized behaves, because you might have like some small data shifts even within data from one client, right? So it might happen that a model from a different client is actually better for a certain image of your data set. So yeah, that is definitely possible.
Okay.
Okay. Yeah, some quantitative results here. Then we kind of expanded this approach by allowing more hyperparameters to be optimized using an online reinforcement learning agent. And here the idea is basically that the agent is getting validation metrics from each client, and based on that is predicting new hyperparameters to be optimized in the next round. And here some baseline comparisons with other algorithms on Cipher 10, where we artificially split the data to follow some. I think it's mainly the label heterogeneity approach here. So using a Dirichlet distribution, we sampled the data to split into 8 clients. And you can see here the number of images is different, and also a number of unique labels on each client is different. And then here how these aggregation weights behave during the training of the federated learning algorithm. This also allows you then to apply this to like some real world data sets. Here it's COVID lesion segmentation in chest CT with 3 clients, and then you can see the behavior. This is actually similar to this is actually the previous work that I described, right? So we can see that this reinforcement agent has a very similar behavior to the prior work, and also uses in relative terms applies very similar weights to these different data sets. Okay, I think we're kind of closing up on time, right? So I will quickly introduce a couple of the software tools that we're also developing. So it's like
20 minutes. So I think you're good on time. If you, I don't know how long you want to spend on this, but still 20 minutes. So I think you're good on time.
Yeah, it should be quick. So let's so we can
I
have
have just one quick question about this auto federated learning. So like what I would like to hear from you is your point on like when you combine these things with differential privacy, right? Like when you do like hyperparameter tuning, you have to at least like kind of quite naive hyperparameter tuning, you would need to query the clients more often just to figure out the proper parameters. But if you want to guarantee like this, you want to have DP guarantees, then you actually have to increase the noise, right? So with that, actually like hyperparameter tuning can actually completely destroy your performance. So did you try to combine these two, or do you have any kind of take on that?
It's a good question. We haven't explored that yet. I mean, one idea here is to do the online hyperparameter tuning, right? So it's actually this is one federated averaging experiment, right? So you're not querying the client more often than the standard federated averaging. So that I think that's probably beneficial to addressing your concern. But still, like how that plays with differential privacy parameters, we would have to explore, I think. But yeah, it's interesting. Yeah, but exactly this topic, right? So now, if you want to do this federated learning in the real world, there are a couple of
we have one extra question from Adriana. Let me just try to unmute Adriana. Please go ahead.
Hi, Holger. Congrats for your presentation. I have a question because I don't know if you have told that before, but your models include some batch normalization layers, because I'm working with federated learning in sleep recordings, and I see a huge gap between the clients and the server when I include this layer. So I don't know if you have any idea on how to deal with this issue.
Right. I think that there has been a couple of works that show that batch normalization doesn't work well in the federated learning setting. So there are these works like FedBN, I think, federated batch norm, which are basically some ways of personalization, right? Each client keeps their local batch norm statistics and doesn't share that with the central server. So in that way, you're also maybe reducing some of the privacy concerns. And you don't have this issue that the global model doesn't work. I mean, in that way, you would only have personalized models, right, for your local data sets. So as I said earlier, this is still like kind of an open question, because like from the regulatory point of view, you might not want to have so many personalized models, but then if you do batch normalization, then it might not work well for addressing the issues where you have domain shifts. So in our experience, I think replacing that with those layers with group norm worked quite well. I think most of the auto ML experiments that I showed based on segmentation models where we don't use batch norm, basically. So all different either instance or group norm.
Okay, thank you.
But yeah, this is a known issue, I think.
Yeah, I know. I
There's
was
also
reading a lot about this thing, but it's really hard to understand.
Yeah, there's also a work that proposes to, instead of doing the averaging, you do a cyclic weight transfer. So you transfer the model from one client to the next, and then kind of do that many times. And that seems to be more robust towards batch norm, because the batch norm statistics kind of keep updating, right? So that might be something to explore as well. We do have an implementation available in our framework as well. And some of the researchers who worked with us on the mammography study, they're really exploring the cyclic weight transfer. Yeah, I think one thing for the community is, right, a lot of the like torch vision models that are pre-trained on ImageNet, they have batch normalization layers. So if you want to use these pre-trained models, then it's kind of a little bit tricky. So we probably need to have more pre-trained models without batch norm to be useful for federated learning. If they can be made publicly available, that would be useful.
Yeah, sure. Thank you.
And then there's a question from Kumar. Yeah.
Sure, go ahead. Sorry, should I look in the chat?
Sorry, I was muted. Okay, so thanks for the talk. I wanted to go back to my question from before. So I have actually two things. One is a more maybe about the regulations, which you mentioned quite a few times. So what exactly are the reasons for which you cannot afford to have personalized models on each hospital? That's one reason, one question. And the second one is more specific, like going back to your slide where you were showing how these adaptive reweighing scheme, it slides towards a particular client. Like you had a triangle and it was sliding towards a particular client. And I'm curious if you've looked into data valuation approaches, like Shapley score-based approaches, to just try and recognize if all you want to do is train on one client and use that model for everyone, but because the client is just like has a really diverse and representative data set, and it might be in fact an overkill to be training on others. So yeah, these are the two questions.
Right. So we are so regarding the first question, as I said, we are exploring personalization as well. So I'm not saying that it's not useful in the cross-silo setting. I'm just saying that it might involve some more thinking with the regulatory processes, how these models are then evaluated, right? If they need to be personalized for different hospitals. Right, because you need to make sure that each of those personalized models is robust. Okay.
Right.
So, I mean, the FDA. I'm not an expert on the the regulatory policy, But as far as I understand, there are actually a lot of people looking into how these protocols maybe need to be updated in order to account for, the recent developments in artificial intelligence and machine learning, and how you can do like online monitoring of models to ensure that they maybe can even be adapted to new data coming in, but don't lose their performance and things like that, right? So these are all relatively open questions at the moment, I think. As far as I know, the FDA is kind of changing their policies as we speak, basically. So this is like a room to be observed for new regulatory guidelines. And the other question was regarding the importance of certain clients. Yeah. So in this data set that we showed, the client with the highest weight corresponded also to the client with the largest data set. So it does these kind of heuristics saying that, if you train more on certain clients, then those model updates are more important for the federated averaging, seem to work quite well with and align with what you get when you try to learn these aggregation weights in a data-driven way.
So I have a question for you. So if I drew the following baseline, which is basically the best of the 3 clients. So I think there were 3 clients there, or the same curve. How would it compete against the adaptive variant and the non-adaptive variant?
So I mean, we show it here, right?
Oh, sorry if I missed it.
I mean, this is federated averaging versus auto fed averaging.
Yeah, but I'm introducing a third baseline, which is basically single machine training, but whatever evaluation happens on each machine. And now you do the single machine as follows: you train on all the 3 machines and take the best model at each time step. So there is never a model exchange. There's a model exchange, but there's never really a gradient exchange happening. Like, it's a non-collaborative protocol almost.
You're saying like at each round you still send the best model somehow?
Exactly.
To initialize each of the clients?
No, you don't need to initialize them. It's just a naive baseline. Probably no one will ever use it. You basically run like an algorithm on like something like SGD or mini batch SGD on each machine. And then you have this validation data set, which you're plotting on the y-axis. And you just look at the best model. And the best model, perhaps in this case, would be the model trained on the client with the most data set. And I feel like that's also a relevant baseline here.
Yeah, one issue we have in the real world data set is that we don't want to share data, so there's no common
so you're not sharing sharing data. I'm just saying there is no non-collaborative baseline here. And looking from your figure, it seems like a non-collaborative baseline might also work well in that particular application.
I mean, we do have these local models, right? So these
I see. Okay.
These show how, like, what performance you get if each client is just training their own model, and then this is the model trained on data set 1 applied to all the 3 client sites, right?
I see.
So this kind of table does indicate that the collaborative aspect, right, does help in building more generalizable model.
I see.
And I think it's something similar we also saw in the larger study with for X-ray, right, COVID chest X-ray, where the generalizability of the global model really went up a lot compared to the local models. Okay, so I was quickly introducing like these different aspects you need to consider when applying federated learning in real world, right? Authentication, secure communication channels, like using TLS, for example, it's a kind of industry standard. But then you also have to have these information security considerations in mind, like applying differential privacy encryption. And there are even hardware solutions that it could be used for federated learning, like confidential compute in enclaves. So to make this kind of technology more easily applicable in the real world, we released a toolkit on an open source using Apache 2 license. So it's like very permissive license that allows you to also commercialize the usage of this tool. And it's basically building on all these experiences we had in the real world studies using at that time, we mostly used our internal SDK to perform these. So now with NVIDIA Flare, stands for Federated Learning Application Runtime Environment. So it's a very general purpose library that could be applied to many industries, right? We don't make any assumptions on the underlying training framework that you want to use. It's Python based, so it's like easy to use, and you can plug in your favorite machine learning frameworks like TensorFlow, PyTorch, or NumPy computations. It's really targeting several users or personas, starting from the FL researchers and data scientists to platform developers, right? So we want to be both supporting research applications and be production ready with this framework. There are several useful features like a simulator for rapid development and debugging. You can do data analytics to get an idea of the distributed data sets, compute like summary statistics, of course, with having privacy in mind. Then we have tight integration with other open source frameworks like XGBoost or Monai, which is for medical imaging, as I mentioned earlier. We have a dashboard that allows you to build up these federated learning projects and deploy kind of access tools for each of the clients and server. So it's like easy to start it up. And then there's a command line interface or notebook type APIs that can be used to run experiments. And of course, everything with real world IT security in mind. And I think the main component to think about is this controller and worker API. So in that way, we can really break down the algorithm to some very simple workflow on the server side and task assignment for each of the client or the worker in this case. And the task could be something like train, right? So the controller assigns training tasks to each client, waits for a certain number of clients to come back, does the averaging of the updates the global model, sends it back, and executes the next task again on the worker. So in that way, it's very straightforward to implement algorithm like federated averaging, but you can really implement any kind of distributed compute algorithms like statistics or even data pre-processing could be done using this concept. Currently, we have a set of algorithms already implemented, starting from some of the classical federated learning baseline algorithms and also some personalization algorithms. And all of these can be extended with like differential privacy or homomorphic encryption, which I think I have a slide as well. Here, a good starting point are these examples like Cipher 10, where we use the simulator to run different algorithms. You can simulate different data distributions and compare how different algorithms behave in that setting. And then we also have some examples from medical imaging, like the brain tumor segmentation or prostate segmentation with using real world data sets. One nice feature is also this filtering. So we can, for example, if we want to apply encryption, we can ensure that every information that is being sent out from the client can be encrypted first And actually there's a local control, so the clients can basically have a guarantee that the encryption filter will be applied to any result that's going out. And that way you can, for example, use homomorphic encryption for secure aggregation. So if you're familiar with that, it basically means that each client is encrypting the model updates. The server doesn't have a decryption key, so it's just computing the aggregate in encrypted space, sends back the encrypted result, and the client then decrypts and can continue training. And in a similar way, we have a differential privacy filter that can add noise to the model updates with some privacy budgeting. In the same way, of course, you can also do like differential private SGD on your local training in the worker if you like. So there is a list of companies who are currently using this for their products. I won't go into detail there. I think we're already over time. But as I mentioned, another nice tool that we're heavily involved in is Monai, which targets deep learning for medical imaging, spanning radiology, pathology, endoscopy applications. And there we have also a working group for federated learning, which is organized by Charashri, Kalpathik Raymer, Daniel Rubin, and myself. So please reach out to me if you're interested in getting involved there. And as part of Monai, we also have a model zoo. So people build models with AI, with Monai, provide pre-trained weights to the in the model zoo, and those kind of models we package as a so-called Monai bundle. So it's a standardized set of configurations that describe how you do training, inference, evaluation. And with NVFlair, we can actually take this Monai bundle from the model zoo and off the shelf apply it in a federated learning scenario using a Monai federated learning integration piece. But the client algo API is actually an open standard, so other FL frameworks could also implement adapters for this standard, so they can use the model zoo bundles in the federated scenarios. Here, I just wanted to mention that we also organized a challenge at MICAI this year, which was one of the first challenges to really apply federated learning in a kind of distributed learning fashion. So the participants didn't have access to any of the data. They were only able to submit their code, and we would have these virtual machines running Docker containers to do the federated learning without having like all the data was in different virtual machines. Therefore, we had to run like a real federated learning protocol, and the participants were only shown the validation metrics to improve the performance. So it's like really the a kind of a fair comparison of different algorithms. Okay, as I said, please reach out to me if you have any more questions. And of course, I think I still have some time to discuss if somebody's around and wants to ask questions.
Thank you, Holger, for excellent talk. There is already one question from Anupan in the chat. Let me just try to unmute.
Hi, Harald. So my question is around the models in the model zoo in Monai. Are they under some license to use, or can be freely used?
I think the license is specific to each model. So you might want to check for the model, but currently the models that we have are mostly, I think they're all free to use basically.
For research.
There might be, I mean, they're definitely free to download and try out. There might be some licenses that specify whether it can be used commercially or not. But I'm I'm not aware of any of those at the moment.
Okay. Okay. All right.
So please check the individual license for each model, but they're
Cool.
all available freely in the model soup. The
Okay.
whole like open, the whole Monai platform is open source, Apache 2 license, and NVIDIA Flare is also open source under Apache 2. So it should be very permissive to use and adapt.
Okay. Thanks.
Yeah. So are there any other questions? Please do raise your hand or just post your question to the chat, and I'll try to unmute you. In the meantime, I would have one more general question for you, Holger. So what do you think is like are the biggest or like most interesting research problems that would kind of enable applying federated learning for healthcare?
Yeah, I think this non-IID issue is still not completely solved. So there, if you have more robust optimization methods that can maybe handle that, and without having to go back to personalization, I think that would be a really good selling point. I think personalization is fine, you know, I have nothing against it, but I think it's somewhat more difficult to talk to clinicians and, you know, regulatory persons to say like, you need to have a personalized model for your hospital rather than using like the general model that is guaranteed to work for all kinds of patient populations, right? So that those kind of issues, I think we need to still resolve. Then I think this was also discussed earlier about things like Sharpley values. How can you measure the contributions of each hospital or each client, right? That will become very important for commercialization as well. I think currently the incentives for some hospitals might not be clear as to why they want to contribute to a federated learning study. I mean, for COVID and these kind of proof of concept studies, we kind of, you know, everyone was motivated to do something to help with the pandemic. So we kind of agree that the model is going to be published afterwards. But if you really want to build a business model around this, right, and you have to basically tell the data providers how they can benefit commercially from training the model, right? So, and that needs to be fair. So yeah, and then yeah, fairness and biases I think are also related to all of these issues.
Yeah, thank you. So there is a question, like if you can stay around there, there is one other question that I see from Kumar. So maybe we can take that. Yeah, please, Kumar, go ahead. You should be able to unmute. Yeah.
Hi again, Holger. So I have a question about the last thing you mentioned, which is the incentives for collaborating agents. So I've been recently surveying this area, and it seems that a lot of the work, so there's not a lot of great work, but a lot of the work is actually trying to use something like model differentiation, like trying to incentivize clients to stay in the collaboration or join the collaboration in the first place by somehow giving them a better model if they contribute more. But based on everything you've said about regulations, it seems like practically you can't really do that. Like practically, that's not a viable way to perhaps incentivize. Because if you're giving everyone a different model, and now not only at the end step, but perhaps at each communication round, just to make them stay, it might again have like regulatory concerns. So I'm curious, like what sort of levers do you see available to a mechanism which is trying to incentivize clients to participate? Like, is money something you see as a viable motivation here? Because often it feels like these clients are not probably participating for money. They're just participating for a better model. So what even is something a mechanism designer can play with?
I think I wouldn't put money to the side. I mean, you know, like in the healthcare sector, you have certain companies who are building AI models and want to commercialize these, but they might not necessarily be the data owners. So the data owner might be a hospital, right, which might not itself have the technical know-how to even build AI models and commercialize them. There are, of course, large-scale hospitals who might play both roles, but in most, if you look like a community hospital, they might have a lot of data, but not any plan on building their own models and applying them in the practice, right? So if they can be compensated with money to provide their data, I think that would be a good incentive for them to act as a client in a federated learning scenario. But the question is like how much, right? Is it just the amount of data that it provides? Or is it also something about the importance of their data set? Which I think that's something where more research is needed.
Yeah. Another thing I've been thinking is, let's say you have to give money to like motivate them, like that's given. How to sort of minimize whatever payments you have to give out? Like, can you algorithmically do something to minimize those payouts?
Yeah, it's a good question. Luckily, I'm not really concerned about the business model myself, but I think it's for the field. We have to consider this.
Thanks.
Maybe if it's it depends. Like if you're starting from somehow a pre-trained model, then maybe the added benefit of using somebody's data is less, right? So then
yeah,
maybe that can be somehow reflected at the price.
Yeah, it's a hard measurement issue, like as you mentioned. Like, there's a valuation question here, and on top of that, the valuation is dynamic. Like it depends on what you have already. So you cannot really just value someone's data based on data. Like you have to do this while being cognizant of what model you have.
Right. Yeah, exciting topic. Please reach out if you're interested in collaborating there.
Cool. Thanks.
Yeah, there's one extra question in the chat that I see by Sinchana asking about the performance. How does the performance compare to the performance of the centralized machine learning?
Yeah, in terms of accuracy, right? I think you mean. So in our studies so far, we were really able to come very close to the centralized model performance. Because there's no theoretical reason for it to be
yeah, I was wondering about that.
Yeah, are there reasons why it's even from my experiments? So sometimes my performance of my federated learning model is even better compared to the centralized one. So I was wondering why this is the case. Is there any reason?
I think that has to do with the stochasticity of the learning process, right? I think.
Yeah.
I'm not sure if somebody has like the theoretical answer there, but I think that you're kind of adding some sort of noise, which is splitting the data, and then that results in more generalizable models.
Okay. And do you think it also depends on if the data is IID versus non-IID cases? Do you think it would differ?
In non-IID, it's easier to get it to work in a centralized setting, right? Because you can randomly sample from all the non-ID data. In that way, you're kind of making it more, you're reducing the non-ID-ness, right?
Okay. I was also considering if it's like a case of bagging, like an ensemble method where you have multiple models, and from federated averaging, we're averaging out the model base. Do you think it's somewhat similar in this case when we use federated learning? Is that why it could be better? Do you think?
Oh, you mean like why it's performing better than central?
Yeah.
I think in terms of the algorithm, it's federated learning is very similar to distributed compute, right? If you do like multi-GPU training on a centralized data set, I think you will observe very similar effects. So I don't think that's the reason.
Okay.
But in general, like the federated learning benefits from having access to larger data and more diverse data sets. Like it's only the federated learning is actually enabling us to have those large diverse data sets in a lot of use cases. For a lot of applications, the data can just not be centralized.
Yeah, so do you think it's maybe not a good comparison, you know, a centralized versus federated in most cases?
No, I think it is important, but I think we're kind of past that comparison already. Like there has been a lot of work showing that you can achieve a very similar performance.
Okay.
So, and now we have if we do these real world studies, in most cases, we cannot do the comparison to centralized training anymore, right? Because the data is actually distributed.
Oh, thank you.
If you look at our early papers, we all like that are based on simulation, we always compare to the central performance.
Yeah, I agree. Yeah, thank you.
Okay, thanks.
So I see there is actually one more question that appeared in the chat. So if you can stay a bit around, I think that might be the last question for you to take. So it's by Shanjian, who is asking that what if you run out of EP budget? But the global model didn't converge yet. So I guess it's related to privacy.
Right. I think this is still an open topic. I think the way we implemented privacy, differential privacy in NVFlare is actually the budgeting is happening at every communication step from the beginning. Right. So you're applying. You're kind of applying the budget to every model update as part of the privacy filter.
Yeah, but if we use a very big budget and I'm little concerned if we add too much noises, so the model will never convergence. But if we communication mode, but I mean communication rounds is too many, so that we need a very big budget. But a big budget will make the noises big.
Yeah, I think that this is definitely a problem. I think it's, from my understanding, it's not clear if what the budget should be. Like from a theoretical point of view, it also depends on what the data is, right? And some data sets might have different privacy concerns. Like if you're learning from social security numbers or something like that, with a lot of like identifiable information, then that has, of course, a lot of higher privacy concerns than maybe medical imaging data of somebody's abdomen, where we don't necessarily have so many concerns, but we don't want to share the data with others, you know. So if they see like very noisy versions of the data, it's maybe less of a concern. I didn't. We have some work on the gradient inversion, which I didn't include in this presentation, but there you can, only in very let's say insecure scenarios we are even able to invert images from gradients that are resembling any of the original data. Right. So in most real world use cases where you have like a large data set and you do like a longer local training on the data set, you don't really leak that much information. So to me, differential privacy is a nice research topic, but I don't know exactly how practical it is at a moment. Like,
okay. Thank you.
More practical is actually the I feel like the homomorphic encryption information theoretic that your data is not reconstructible, right? And it doesn't actually model performance.